Thank you everybody and the organizers. So I'm going to present this result mainly, that torsion-free abelian groups are Borel complete. I will define the notions, although maybe some of you know what Borel completeness is, although maybe not under this name. But actually, I would like not to speak only about this result, but about the ramification of this, and even mention what inspired our solution, because actually we were working on another problem, which is this notion of copianity, which appears in part 3. So actually is the construction of this kind of groups. Copianity is a kind of rigidity condition that allowed us to develop somehow this technique that led to the solution of the problem, which I will introduce. So somehow all this will be in the tradition of construction of rigid structures. The co-author of this work is Aaron Shela, and he has a long tradition of construction of these rigid structures, and so it's definitely in this tradition. So in part 1 we look at this main problem, a very short idea of the proof, because unfortunately it's rather complicated, the formalism that we set forward, and then I will talk about these ramifications that inspire the solution. They are not only ramifications. Anyway, so we go to the first part. Now a little bit of motivation, at least the way Saron and I see the problem is maybe from a more model theoretic perspective in some sense, and we write in the introduction, I like this passage, that the Borel completeness of countable abelian group theory is particularly interesting from the perspective of model theory, as this class is model theoretically low. So abelian group theory is stable, while, for example, other cases like all groups or fields, in these cases we have a stronger notion than Borel completeness, which we will define later, because there we can interpret first orderly graph theory. And so such classes are unstable, in fact, because graph theory is unstable. So here we have to do a much more delicate construction. And okay, this is the framework that is used in the descriptive set theory of countable structure that maybe most of you know, so I will only mention what is it that we do. So we fix a vocabulary, a language, in the sense of model theory L, and we consider the set of structures with domain omega of L structure. Now, this admits a standard Borel space structure, which I won't define how we do it, but maybe most of you saw it. And then any Borel subset of this space naturally endows a Borel structure. And so we are liberal in this respect, and we talk of these Borel spaces. So for example, the language that we will consider is only the language of group theory, because this is only about groups, this talk. And so we have the identity, the multiplication, the inverse, and then we can consider the class of groups, for example. This is even first order of abelian groups, of torsion-free abelian groups, which will be our interest, and of n-nilpotent groups, which will play a role at the end. Anyway, these are all Borel subsets. So this is the spaces that we are interested in, and we will talk about. And so some notation, because will be used. GP denotes the class of groups, AB the class of abelian groups, not AG, AB for some reason we use, TFAB torsion-free abelian groups, which I recall what they are. And then when we have a class of structure K and a lambda cardinal, then we denote by K lambda the set of structures with domain lambda. Now we have two notions of reductions, and I just make this precise to avoid confusions. So we have a notion of reduction between subsets of Borel spaces, a notion of reduction between equivalence relation on Borel spaces. So I will now introduce the first and the second because they both interlace in some statements, so it's better to make this precise. So we have two standard Borel spaces, x1 and x2, and y1 a subset of the first, y2 a subset of the second, and we say that y1 is Borel reducible to y2, or maybe just reducible, and I denote it with less or equal r, when we have a Borel map from x1 to x2 such that for every x in x1 we have that x is in y1 if and only if bx is in y2. And we can actually use this instance of an instance of this notion when we have a product space, and so we can consider an isomorphism relation as this y1 or y2. So we can reduce isomorphism relations in this sense. But actually, when we talk about isomorphism relation, we will be interested in the more classical notion of Borel reducibility, which I will later introduce. But both play a role, so I have to introduce all this. Anyway, then, once we have this, we can talk about a set being complete analytic or complete co-analytic, which is something that we will do, it will play a role. And then we say if all, for example, is complete analytic, if all the analytic sets reduce in this sense to that set. Now, so we go to the second notion of reducibility, which is the one that is behind the notion of Borel completeness. So this is maybe the main one. And here we have, again, two standard Borel spaces, x1 and x2, and then we have E1, an equivalence relation on the first, E2, an equivalence relation on the second. And for us, actually, the equivalence relation that we are very interested in are isomorphism relations. And we say that E1 is Borel reducible to E2 when there is a map from x1 to x2 such that if x and y from the first space are equivalent, this happens if and only if bx is equivalent in the second space to by. So the point is that you can, as I said, consider E1 and E2 also with respect to the other relation, reducibility relation. But the point is that in this case, the domain of the function is x1, while in the second case is x1 times x1. So let's just keep this in mind and avoid confusions which may reasonably arise, because we will say something like an isomorphism relation is complete analytic, but does not give rise to a Borel complete class, which I will introduce. So we will use both of them in the same sense. Anyway, so now we go to the central definition, which is this one, of a class being Borel complete. Some people reasonably complain that this name is an old name. I understand it's more in the logic tradition, and with Saran we choose to use this, but I'm very liberal, so maybe the isomorphism relation being S infinity complete makes some of you happier, which is reasonable and is fine. Anyway, we have K1, a Borel complete class of structures with domain omega, and then we have an isomorphism relation on Y1, and then we say that K1 is Borel complete if you take any class of countable structures, then the isomorphism relation on this second space is Borel reducible to the first. So it's maximally complex in the sense of isomorphism relation of countable structures, no less and no more. So it's really the intuition that is written that read isomorphism relation on K1, the Borel complete class, is as complicated as possible as an isomorphism relation. This should be stressed very strong. So, and now what I mentioned about mixing the two notion of reducibility, so not to avoid confusion, I did all that. Because if you have a Borel K, a Borel class of structures, if K is Borel complete, then its isomorphism relation is complete analytic subset of K times K. But the converse need not hold. And the canonical counterexample, the first one that is crucial at least, is very relevant to us, is in fact the case of abelian P groups. I will even remember what they are. because the isomorphism relation of abelian P groups is complete analytic, but the class of P groups is not a Borel complete space. So we have abelian group theory is the topic of this talk. So anyway, we have a lot of examples of Borel complete classes. Of course, we have countable graphs, which is what we will use in our reduction, in our main theorem, linear order, trees. And torsion abelian groups are not, because the P1 generalized to all torsion groups. Notice that nilpotent groups of class 2, which are the closest thing on Earth to abelian groups, without being abelian, are actually Borel complete. These are all well-known things, even from the 89 paper, which is the first paper on this reduction that at least that I think introduced explicitly this kind of notions. So you see, abelian P groups are not Borel complete, but nilpotent groups of class 2 and exponent P are Borel complete. So really the question is, are abelian groups at all Borel complete? And in particular, even torsion-free abelian groups, which are a crucial subclass of abelian groups. So this is a question from the 89 paper, and there they say that they conjecture. Anyway, this was completely open till last year or this year. In fact, they didn't even know if this relation was complete analytic as a subset. But this was solved before our work. Now, I will introduce the notion of abelian group theory. Maybe some of you don't remember, which is reasonable. So, an abelian group, so G in a B means G is an abelian group, is torsion-free when for any non-identity element we have, and the natural number n, we have that n G, so G plus G plus G is different from 0. And here we have another notion which will play a role of rigidity, and G is rigid when its automorphism group in the context of abelian group theory is as simple as possible, because it has the identity map and the function that sends G to minus G. These are always automorphisms, and so being rigid in this context means having only these two automorphisms. Now, we said that we will talk about torsion-free abelian groups, so let's look at examples. Of course, we have Z. Of course, we have Q. Then we can take direct sums of Z or direct sums of Q. And then we can take subgroups of direct sums of Q. Now, the claim is, or the fact, that the reminder is that these are not examples, but this is a list in some sense. So I just recall this briefly, so that you can see all torsion-free abelian groups as subgroups of copies of Q, of sums of Q, so it's something very familiar, I think, to all of us. And behind this, there is surely the notion of divisibility, which is crucial. That's the alpha and omega of everything we do. And because it's all about encoding divisibility very, very, very carefully. Anyway, we have G an abelian group, an element G, a natural number positive, and we say that G is n-divisible if there exists H in G such that NH equals G. So this is a root of unity in multiplicative notation. And now the group G itself is divisible if for any element and for any positive n you have this. So it's as divisible as possible, a divisible group. And now, so it's a very well-known fact that every torsion-free divisible group D of rank alpha, I didn't define what rank is, it's a little bit technical, but you can think of it as having a basis, really formally, and so it's the size of a basis. And is a direct sum of alpha copies of the additive group of rational numbers. So, really, subgroups of sums of Q is not an example, but a description of the torsion-free abelian. So, it's really all about this. You have Z that has the minimal amount of divisibility and Q that has the maximal amount of divisibility. So you have Z plus Z as the minimal amount of divisibility in rank 2, and Q plus Q as the maximal amount of divisibility in rank 2. It's really like this. So the point is constructing things in the middle. Well, the middle should be into here. This is the whole point. But we will get to that in a bit. And okay, so I mentioned this torsion term several times. Maybe you remember it for the course in algebra, but anyway, it's easy to define. We say that a group G is torsion if all elements have finite order. So it means for every G there is a positive n such that Ng equals 0. And we are also interested in a canonical subgroup of a general abelian group G, which is tor G, we call it. So the torsion elements of G is a subgroup, and G in G, this is a set of G in G such that there is a positive n such that Ng equals 0. And we are also interested in torsion P of G. So we have P that is a prime number, and then we have the G in G such that there is a positive n such that Pn of G equals 0. So these are all subgroups. So for example, a group is torsion if tor G equals G, is a P group if tor Pg for a specific P is P. This is nothing else. And now I think I have a little table of what's going on. Yes, so this is before our work. We have the torsion groups that, as I mentioned, are not Borel complete, although I have an isomorphism relation which is complete analytic. Then we have the torsion-free Abelian groups, and at this level there is the question of Friedman and Stanley. And then there are the mixed groups, which I didn't define, but just groups that have both torsion and non-torsion elements. Okay, I mentioned here that 3 does not reduce to 1 and 2, but we can leave that there. So now the problem is really if the Borel space of torsion-free Abelian group with domain omega is Borel complete. So now you have all the terminology to understand both the algebra that is behind this and the descriptive set theory, those basic definitions. And so this was posed by Friedman and Stanley, and then I describe a little bit the history because it's an important history. So the first one to work on this that I know of was Hjort. And in this reference, he proved that any Borel isomorphism relation is Borel reducible to the isomorphism relation. So in the sense of Borel reducibility, the second one. Yeah, as a subset of the product space, I mean, that is Borel. Any isomorphism relation that as a subset is Borel reducible in the sense of these two, which I made precise because I spent quite some time on the distinction. So I think, yeah, so I mean really in the, I think the most natural sense. So it's above all the Borel isomorphism relation. This is what your proof. And in particular, it follows that it's not Borel, the isomorphism relation torsion-free Abelian group of domain omega. So, but he left open the question, for example, is this, of course, is this a Borel complete class? And also, is it complete analytic in the sense of the other notion one? So now I try to make this precise. And well, here I write that the problem resisted further attempts because I think that for quite some time there was no progress. But then the community moved to another very interesting problem, and now I'm going to talk about the works of Thomas because I think they must be mentioned in this area. But I try quickly only mention it. So the problem moved to the question. So there is this notion of rank that I mentioned, though I didn't define, which uses basis. So if you consider the isomorphism relation on torsion-free Abelian groups of rank n or of rank m, where m is strictly greater than n, is the first Borel reducible strictly to the second? So do we actually have a tower of isomorphism relation complex, more complex, complex? And this is a very interesting question. And both this question and the question that we face is actually, I mean, this genuinely comes from group theory. just to convince yourself, this is taken from, I think, yeah, the chapter of Fuchs' book on torsion-free abelian groups. They really complain somehow that although for the groups of rank 1, Bayer gave some invariants which are satisfactory, for rank 2, rank 3, I mean, he says there are constructions that you can do, but there isn't a general framework to it. And not at all if you have infinite rank, which is what we will be interested. So this is really, one could take this, is of course a crucial reference, and try to make sense of this, and using descriptive set theory is of course the right way to do it, because it deals with system of invariants. Now, so what Thomas did is that he actually solved the problem and proved that the isomorphism relation on the torsion-free abelian groups of rank n, and now I'm reading the first theorem here, is strictly less complex than isomorphism relation of n plus 1 rank. And actually he showed something stronger, that if you consider the isomorphism relation on torsion-free abelian group of rank n, which are rigid in the sense that I introduced, that's why I introduced it, then this n plus 1 rigidity isomorphism is not Borel reducible. The isomorphism relation rank n. Now this is, of course, it's strictly connected to our work, but it's very different, because on rank n, on finite rank, the isomorphism relation is Borel, on infinite rank is not, but of course this is on the way, and show the mathematical complexity. These were appreciated papers, and very nice solution. And but this is just star. It's written there, and I mentioned it. It's the isomorphism relation of abelian group rank n, which are rigid, which is another notion that I define. Now, okay. Why am I here? Okay. Now. Okay, let's get to it. So, but what about the whole class of torsion-free abelian groups, so finite and infinite rank? Is it actually Borel complete or not? Now, the last crucial advance that I know of is a paper of Downey and Montalban that actually showed that this isomorphism relation is complete analytic as a such. So this, I mentioned that this was not even known. This is a necessary but not sufficient condition. They actually showed this, and of course it's an important step, but it surely is not sufficient to solve completely the question. And then 12 years or something after this paper, so this is 21, so in February we announced the result that we actually have a solution, a positive solution. We have an explicit construction that's from graphs with domain omega to torsion-free abelian group with domain omega that is actually continuous, such that taken two graphs, they are isomorphic if and only if the torsion-free abelian groups are isomorphic. So this is a solution to the problem. Now, unfortunately, the proof is very, very technical, in the sense that we have to devise a specific frame, a way of constructing a torsion-free abelian groups that uses some, I wouldn't say made up, Saron says some sort of free system, but one has to be careful. And so I should introduce a lot of notions. I mean, a lot of specifically defined notions, let's say, to actually describe this, and I want to. But the idea of the proof, I mean, this is somehow is contentless, because anyway, this had to be done. I mean, not this universality bit, but the fact that there has to be this middle point of divisibility. I mean, but at least I hope it gives us a flavor. So, but this universality specific bit, this is not, is peculiar. I mean, it doesn't change, but it allowed us to simplify our work. So of course, we want to construct a function, a Borel function, continuous from graphs to Abelian, torsion-free Abelian. But we don't start from a graph and do it directly. We first take the countable random graph, which, as we all know, is universal for graphs with domain omega, and then we construct a universal domain for our construct. Now, M, Boban. Well, yeah, I will tell. So, well, let's say somehow it's defined there, but let's look at it. So we have G0 Boban, which is just sums of Z, of copies of Z, and we have X many. Okay, so X is just the index set, but it's important that it's this X because we have to encode a lot of stuff on this X. This is the whole point. And so we have, so this is the minimal amount of divisibility in rank, in infinite rank, omega. And then we have the maximal amount of divisibility, so G0 and G2. So what about M? M is in the background. He's sitting here and he always appears. But the point is that using this M, Yoko, we will construct a group G1 which is in the middle. And this will be universal for our construction. In what sense? In the sense of, in this sense, this is something very natural. I mean, it's not, the solution is not here. This is the general strategy. Now, for any subset of M, so for any as M is universal, this suffices for the construction. For any U that lives in M, so subgraphs, infinite subgraphs, let's say we define a subgroup G1U of this universal G1. So first we construct the universal, and then we take for each graph the, I mean, of course we give out. Okay, this is my fault. I should have used another word, another letter, absolutely. So that's like, it's supposed to be a calligraphic cube, but I see now that I failed to maybe. U, no, U ranges. U is a sub that is written there of the random graph. X, as I said, is just a basis, for G0 and for G2. Yeah. No, X is not it's not related. X is I mean, you have graphs live here, groups live there. We are constructing something in the middle, and you have a basis for this sandwich. Below, it's like vector space. It's a basis, really. It's really in this sense. I mean, you can really think of it this way. You just add rationals. So a basis is just, you add rationals to the elements. That's nothing else. What's a basis in Abelian group, Torsion-free Abelian group? So we construct this universal G1. Then for any U, now a subset of the random graph, we take a specific subgroup G1U, and this is our construct. Okay? I think it makes some sense. So what we want to prove, of course, is if U and V, so that's a U and then Boban, and that's a V. If U and V are isomorphic, they are two graphs. This happens if and only if the corresponding groups are isomorphic. So just to make this even more precise, then we take an H, a graph, then we map it continuously into a specific way in a subset of the random graph, and then we apply this construction, and so we have really what we want. Of course, the point is not this. The point is actually doing it. And this, as I said, won't be mentioned, but I did this little drawing, maybe it's nice. So, as I said, the point, and I won't define how we do it, but just to give the idea, is to encode things in this X. X is the basis. So imagine a vector space, so we are encoding things on the basis of the vector space. And so we have this M, and we have partial automorphisms of M. So for example, we have this green part we send to the other green part, and the yellow part to the yellow part. So G0 is the first and G1 is the second. And now the point is that this X is a partition into infinite sets of our X. And then we define some partial functions to these pieces that respect this information of the domains. And then, but these are just partial functions, really. Now the point is that we will extend, when we define the group, we define very carefully these two actually partial functions of the group. As this is the basis, there is a canonical way of extending them. But the crucial bit is to encode this partial function. But the technicality of how we do it is very, very delicate. And the whole point was really achieving this, actually being able to. So now you can complain rightfully because I don't define G1, but to define G1, I really should introduce a lot of technicality. But this is the basis, so at least you have a flavor. Okay, now though I wanted to mention these other problems because I think they are interesting and maybe they are not so well known, although the interaction with abelian group theory and set theory, of course, have a very long tradition, and Shelah was certainly in this tradition, but we discovered this problem that we really like. So, and also it's nice, I think. So we have a group. This is a definition of words for any group, and we say that G is co-Hopfian. Let's look first at co-Hopfian. When for any endomorphism of G which is injective, then this is surjective. So whenever you are injective, you are automatically subjective. And so this means that you don't have, if you think about it, that you don't have a proper isomorphic subgroup. This is what it means. And the notion of Hopfianity flips injectivity and surjectivity, and means that you don't have a proper quotient isomorphic to the group. So this is a rigidity condition, if you think about it. So not having a proper isomorphic subgroup in particular is what we will consider mostly, and it's a natural notion. And we actually see it in, although maybe not with this name, in the courses in algebra when we do them. Because, for example, the group Z is Hopfian but not co-Hopfian. Because, for example, the map that sends n to n, to 2n, sorry, is a wind test that is not co-Hopfian because 2Z is isomorphic to Z and is a proper subgroup. And on the other hand, if you take a surjective map and you reason about the kernel, it has to be injected. On the other hand, the group ZP infinity, the P-proof group, which can be defined with the infinity generators G1, G2, and the P of G1 is 0, P of G2 is G1, P of G3 is G2. This is a classical group, divisible P group of rank 1. Then this is Hopfian, but this is co-Hopfian, but not Hopfian. So the other phenomenon. Now, so the point, what we will be interested in is in a classification problem for Hopfian or co-Hopfian groups. So here we are in the tradition of the first notion of reducibility. So how complex is a subset of co-Hopfian groups in even the class of groups with domain omega, subset of groups with domain omega. So, and first we think, okay, let's look at torsion-free abelian groups. But there is a very well-known fact that G is co-Hopfian if and only if it is divisible of finite rank. So it's just a finitely many copies of Q. So it's certainly Borel and very easy to describe. Now this doesn't work anymore. If I click on it, it goes okay, so I will click. So now the point of these slides is to give a background of these co-Hopfian groups. And using this, yes. So there is this fact that if G is an abelian group and is co-Hopfian, then its torsion subgroup is at most continuous. So it can't, of course, a P group or a torsion group, which is co-Hopfian, it can't be too big. They can't be arbitrarily large. And furthermore, it was proved that there are no coefficient P groups of size Aleph0. Okay, so P groups, they have to be a size at most continuum, and there are no in Aleph0. Of course, this leaves open the question, are there coefficient P groups abelian strictly between, above Aleph0 and at most the continuum? And it was proved that for lambda the continuum there are. And the question then arose, what about other cardinals strictly between Aleph0 and 2 to the Aleph0? And this was shown recently in 2015 to be independent from the Aleph0. Now this is the first piece of literature that we want to improve. And I will mention that cardinal invariance will appear. I say strictly between, yes. Okay, because, yes, okay, I see. I should say more specifically whatever. That they can, there can be one strictly in the middle, or there cannot failing CH. Okay. Sorry, okay. I should have been more precise there. Okay, so this is about the Hopfian bit. Now we want to mention the Hopfian bit, because also this connects with the construction of Saron. This is the first construction actually where he introduced black boxes, which is then at least according to him, behind all the construction of many models in model theory. I mean, it's really this kind of constructions are very important to him. So he proved, solving a problem in abelian group theory, that for every lambda there is an torsion-free abelian group G, which is endo-rigid, which means that for any endomorphism f of G, there is an integer such that this f is just multiplication by m. Yes. So, and f is onto if and only if m is either 1 or -1. So, in particular, an endo-rigid group is Hopfian. So, this was actually how it was known that there were Hopfian groups in every cardinality, even finite is trivial. And he used this notion. But this construction actually uses stationary sets. He uses black boxes. And we want to look at an effective construction of this. We want to make this construction effective. And this connects to another tradition that he, Fuchs, Goebel, and others were very interested in and still are. That is the preservation under any forcing extension of the universe. So you don't want just to be Hopfian, but you want to be Hopfian in any forcing extension. For example, there is this problem which Saron keeps coming back, that he really likes, is the problem of existence of absolutely indecomposable groups. So they remain indecomposable in all forcing. Absolutely, it's this notion, sorry. Yes, I didn't say. The preservation under forcing extension we call absolute something. So you know absolute something is absolute if. And so if you can split an abelian group, this is the problem that is solved. But so of course here we focus on the notion of absolute Hopfianity. So we know there are, but can we make the construction absolute? Yes, sir. Any forcing extension. You mean no. You mean like using so you mean making this is it makes the problem trivial? Ah, okay. Yes, you can reduce it like using the Levy, for example. No, it does. it does, for example, in the Hopfian case. So we have these, then, three tasks. So on one hand, we want to improve this theorem in ZFC that there are no co-Hopfian phi groups of size Aleph 0 or strictly above Aleph 0. So we want to understand better. So using cardinal invariance. And then we ask, this is very natural as a question, if there are arbitrarily large co-Hopfian groups. I'm surprised that this in fact was not in the list. And then on the Hopfian side, as there are in every cardinality, we want to do the best we can, so make the construction actually effective. So this absolute. And we achieve to some extent the three of them. This is also improved, but this is work in preparation, so I mention it only later. Anyway, so we prove that if G is reduced, it means it doesn't have a non-trivial divisible subgroup. Anyway, it's a standard assumption because otherwise it reduces to this. And G has size below the continuum and at least Aleph 0. Then it's sufficient that the cardinal invariant P is strictly above the cardinality of G to make such that if you have a torsion P part of the group infinite, then you are not co-Hopfian. In particular, if the group is a P group, of course, this is satisfied. So it shows that there are no infinite reduced P groups of size strictly between P. Strictly below, sorry, P. So this gives a lot of information. And now Saron is continuing this on finding the right cardinal invariant to do this. Because P is good, but good enough, not good enough. And a crucial point is that we realized that there are, for certain cardinals, so if lambda is above continuum and strictly below lambda to the Aleph 0, then there is no co-Hopfian group, abelian, of that cardinality. So surely, so this leaves open the problem of construction arbitrarily large. But on the other hand, he has another result that you have to use black boxes because you cannot do this absolutely. And now we also solve this. So this is becoming an if and only if. But this we didn't write up yet. So. And on the other hand, we achieved to do this to effectivize the construction that gives Hopfian groups in every cardinality. So we can do this absolutely. And now, I don't know, when I have to stop, maybe you can tell me. Okay, so I can mention, I go back to the countable side now, in 3-4 minutes I can mention this. And we ask, what about countable co-Hopfian groups? Because, for example, in that paper in transaction that I put there, they actually try to classify them. And, well, they tried to classify the abelian ones. And actually, this was a question of Thomas. If the co-Hopfian groups are complete coanalytic in the space of all groups with domain omega without restriction. This is what inspired our work. Because in trying to solve this, we invented that technique. And this we solved in the end. Proving that if G is nilpotent of class 2, which is the closest thing to being abelian, we don't even have to read the definition, then the set of co-Hopfian groups is in that space in nilpotent groups with class 2 of domain omega is complete coanalytic. It is as complex as possible. What's interesting is the abelian case. And we leave open the question if the co-Hopfian groups are complete coanalytic. But we reduce the problem to a very concrete problem. So this is what we do. We have a co-Hopfian group countable, abelian. Then we can prove that for every prime P, we have that the torsion part has to be finite. And then we also prove that G embeds in the profinite group, which is just the product of all these finite groups. Because for any P, you have a finite group. And actually, G has to be a subgroup of this, which is also a completion in terms of topology. So the problem reduced to a very concrete problem, because now the point is that you fix this, for every P, you fix a finite P group, and then you take the product, and then the point is understanding subgroups of this big group. So the problem reduces to this. But this we didn't yet, at least, achieve. And, okay, I think, well, maybe I end here. We also were able to prove that the rigid abelian groups are complete coanalytic. So this notion of being rigid, which appeared in the work of Thomas and stuff, if you take that as a sub, this is as complicated as possible. And actually, we do more, because we prove that all the groups in the range of the Borel function are Hopfian. And then if the tree is well founded, because of course we are reducing trees to torsion-free abelian groups, then BT has only the corresponding group trivial onto endorphins, so it's even more, and 3. And by the way, it is open if Hopfian torsion-free abelian groups are Borel complete. That we couldn't solve. And yes. Excuse me? Yes, trees with domain omega, sorry, now. With domain omega. Or levels omega, but yes. So this we could do, but in fact this, you see, the Hopfian stuff is that we were trying to prove that torsion-free abelian group Hopfian are complete coanalytic, but this for the moment we put on hold. It's difficult. You take any tree with domain omega, and then if you don't have an infinite branch, then you have something. If you have no, if I mean, they are well, the predecessors are well ordered. Yeah, trees in the sense of, sorry. A level, you mean? Sure, yes, sorry, but you asked about the predecessor. Yeah, yes, I think, I might. Yeah, non-well-founded, it means, I mean, it depends how you look at it from above, below. Anyway, if it has an infinite branch or not, that's what you care. Is this complete coanalytic, you can just, this is what you do at least. So it's just infinite branch or not. You can recognize it's like well-founded, even linear orders, that's how you do it. And okay, I think I'm out of time. Anyway, this is what I had mentioned, that actually we can improve this to an if and only if about the existence of uncountable ones, but this is a work in progress, and it goes in another also. It needs another notion. But I think I'm out of time, so it's fine. I end here, and I think I have a last slide. Yeah, okay. Of course.
Great, thank you very much. Well, first of all, thank you for this very interesting talk on a very important result. I'm interested in classification of uncountable structures, where of course the Borel, the descriptive set theory is very different. However, the techniques that you use, which are basically using the graphs and then reducing things to reducing graphs to your problem, I think there is no reason to think that you couldn't do these techniques as well with uncountable graphs. And for example, with Piotr, who is around, we had some questions about measures, finitely additive measures on the space of the form 2 to the kappa. We classify them on, we show that they are unclassifiable on 2 to the omega. So this problem as well, you could be looking at uncountable torsion-free groups. Have you thought of this type of problem?
Yes, I can answer. So first of all, there is a paper of Shela and Laskowski that I don't know if all of you know, but it's very interesting, that he actually talks about lambda Borel completeness and these kind of reductions for higher cardinality. And there they do, and this also connects to potential isomorphism and other things. And even, Mirna, we realized, we think it's open, maybe somebody can tell, if torsion-free Abelian groups for an uncountable lambda is Borel complete in this sense or not, we don't know. What I find more interesting is if torsion-free groups, which in omega are not Borel complete, because there the Ulm invariant theorems, Ulm theorem fail. So maybe you can actually. So to me, I think this is what you asked. This is certainly of interest, and we might, if I convince her, but we discussed this too, we might go into it. I think it's reasonable, no, to ask. And so yeah, this is clear to me, and also other problems, of course.
Great. That's interesting. Does anybody want?
So if there are no other questions, then we thank our speaker again.
Okay.